All right. So I'm super bored right now. It's 12:16 um at night, and I wanted to put out a video because I wanted to do organic chemistry and I needed an excuse to do organic chemistry. So my excuse was to make a video for our YouTube channel. So this is just going to be predicting substitution versus elimination reactions. And this is one of the first, I think, most difficult things you'll actually do in OChem. Probably the first thing after stereochemistry. So let's get right to it. So for this first reaction, we have this cyclic compound, and we look at our reagents, and we know sodium hydride. We know hydride H minus is a strong base, so we'll write that strong base, but it's also a weak nucleophile, right? And it has to do with its size. It's super small, and I know it's kind of contradicting. Like, you would think smaller nucleophiles are easier to attack, but for hydride, it's so small that it's not a strong nucleophile. It's a weak nucleophile. So with this, you're primarily going to get elimination product, or you will probably only get elimination product. So now we know that this is elimination, so it's going to be, and since it's strong, it's going to be E2 mechanism, which we're not going to worry about the mechanism right now. We're just going to predict the products. So now we know it's elimination, so we need to identify our beta hydrogens. We know that there's beta hydrogens here, and there's also beta hydrogens there. And what's important for other problems involving elimination reactions is that your beta hydrogens need to be, for cyclic compounds like cyclopentane here, they need to be transdiaxial, and for acyclic, they need to be anti-periplanar. So that's important to remember. But in this case, all of our beta protons are going to be either transdiaxial or anti-periplanar. So you're going to get multiple products. You can get a product where this beta proton is removed and you get a double bond placed right here. So we'll draw that first one out. So, oh my gosh. Yes, something like that. This is still on a wedge, and this methyl group is now on a line because that carbon's sp2 hybridized. We know sp2 hybridized carbons are going to be planar, right? So that's the first one if you were to remove this first proton. So in fact, let me color this. So that corresponds to that one. This next proton here corresponds to this product if you were to remove it and go through an E2 reaction. Man, that's so hard to draw. So your methyl would be on the plane, and then you would end up with that. So that's if you remove that proton. And then the last proton occurs when you remove, this is going to be your minor product just because it's the least substituted alkene. Man, I'm sorry, guys. And then it occurs like that. Again, I encourage you to go through the mechanism for this. I'm not going to do it just for time's sake, but there are some problems later on in this video we'll do the mechanism for. So that's for the first one. For this one, we have some primary, so it's always important to know the type of alkyl halide. So I didn't do it on the last one, Or did we have an alkyl halide? Yeah, it was iodine. So this one's primary, right? We know primary alkyl halides, they mainly go SN2, right? They can go E2, but that's usually in the presence of a strong sterically hindered base. Strong, bulky base. But for sure SN2, right? Primaries love to go SN2. And this is in DMSO, which is a polar aprotic solvent, so that's going to further show that this is going to go either SN2 or E2. And sodium ethoxide is a strong base, strong nucleophile. So the fact that it's a strong nucleophile and this is primary, our major product is going to be our substitution product. Okay? So you would get this as your answer for this substitution product. And then this stays there. Nothing happens to these methyl groups over here. So this would be our major substitution product. So major SN2 product. And I would say, and I know the textbook probably says that primaries can go E2. It's probably a super minor product just because we know on the spectrum substitution reactions, at least SN2s, prefer methyl halides, right? So something like this, CH3I, that would be methyl halide. That reacts faster than a primary alkyl halide in SN2, which reacts faster than a secondary alkyl halide in SN2. And we know tertiary alkyl halides do not go through SN2 because of the steric hindrance. E2, on the other hand, E2s prefer tertiary alkyl halides, and they react fastest with tertiary alkyl halides, and it has to do with the more stable product is formed, right? So then next would be secondaries, and then you would have that reacts faster than primaries, and then methyl halides don't go E2 for obvious reasons, right? Because a methyl halide looks something like this, and you know elimination reactions are forming a double bond between two carbons. If you only have one carbon, there's no way to form a double bond between two carbons, all right? So these don't undergo their respective reactions. So like I said here, this is primary. In terms of the ranking, SN2, the primary is the second most reactive, whereas in E2, the primary is the third most reactive. So it's actually the least reactive for all of them. So major product is your SN2 product. Next, we have this thing here. So sodium hydroxide is a strong nucleophile and base. And we have a secondary alkyl halide. So this is the things I do during a test. I kind of just label whether our reagents are strong or weak, if they're strong nucleophiles, if they're strong bases, or if they're both, or if they're strong nucleophiles and weak bases. It all depends on the scenario. So we know hydroxide is a strong nucleophile, strong base. We're dealing with secondary alkyl halide. Like we did up here, we know secondary alkyl halides can go both SN2 and E2, but because of this ranking, E2 would be the major product over SN2, but they're still competing. So you still get a little bit of both products, but if you were to perform this in a lab, you'd probably expect to get more of your E2 product. So we'll do both products, and we'll just label which one's major and which one's minor. So our major product is our E2 product, and we need a beta proton that happens to be anti-periplanar, since this is acyclic. And that's exactly what we have here, right? Because our bromine is on a dash, or on a wedge, and our beta proton is on a dash. And we actually have two beta protons. Important to note. But we're going to draw the major product one, which follows Zaitsev rule. So major product E2, the major E2 product would look like this. So it would be 2, 3, 4, 5, 6. That's now on a line, and then you get your double bond there. So this is major E2. You do have a minor E2 where your double bond would be placed here. But we're just going to do major products. And then your minor SN2 product would be this one here. So 2, 3, 4, 5, 6. This is SN2. We know SN2 reactions occur with the inversion of stereochemistry. So if that bromine is on a wedge, this hydroxide is going to attack from the backside. So OH minus, it does something, it comes from the backside and then forms a bond with that carbon, and then bromine leaves, right? So you're going to get your OH, your alcohol, on a dash. Okay? Let's see. All right, this one is, so we have a tertiary alkyl halide, and we have a strong nucleophile plus base, right? Off the bat, when I see tertiary alkyl halide, and then I see a strong base or strong nucleophile, I immediately toss out SN2, right? It has to be either SN2 or E2, but we know it can't be SN2 just because of steric effects, right? You can't, this nucleophile OH minus, it would be extremely difficult for it to perform a backside attack on this alkyl halide just because of the steric effects of the steric hindrance of all these R groups attached to the electrophilic carbon right here. Okay, so what actually happens is you're going to have an elimination reaction. So you need to identify all your beta protons, and it turns out you only have one beta proton, and it's right here. As we see here, there's no beta protons here. We have 2 methyl groups and then an ethyl group, and we have 3 methyl groups on this carbon, on this beta carbon. So your only product is going to be the E2 product that looks like this. So 2, 3, 4, 5, 6. That goes there, that there, and then this looks something like that. All right. Boom. We got one more for this video, and then I'll probably make the other video for the other problems. There's all these other problems. This one right here is a problem asking, you get both the same products, but you have to figure out which reaction is better to form the product, the desired product. So we'll do that one later. This one, you have secondary alkyl bromide or alkyl halide, and you have your strong nucleophile plus base, right? So if it's secondary, you can go both SN2 and E2. But your major product would be your E2 product, although you're still going to have some SN2 product lying around, okay? So we'll draw both of them. So your major E2 product would be here. If it attacks this beta proton to form the Zaitsev product, right? So you get 2, 3, 4, 5, 6, like that. That's our E2. SN2 would be if the hydroxide performed a backside attack on this electrophilic carbon, and bromine leaves to get 2, 3, 4, 5, 6. And then you get your alcohol protruding from the backside. Inversion of stereochemistry. All right. So just for fun, let's go ahead and determine the configuration of this chiral center here. So we prioritized our alcohol based on atomic number, right? So 1, then you get the second here, 3, and then your hydrogen is on a wedge. That's our 4. So we're going counterclockwise, but since our hydrogen's on a wedge, we need to reverse it, right? So if we're going, this shows R, but since our hydrogen's on the wedge, we flip it. So this is actually S configuration. So let me erase that. Oops, didn't want to do that. There we go, there we go, there we go. Okay, so yes, this is S configuration, which means before it must have been R configuration, and we can test that to be sure. So 1, 2, 3. Our H is on a dash, so you go counterclockwise. That's gonna give you R, and there's no flipping needed, so yes, it was indeed R configuration before the reaction. So that was just for fun. And yeah, that's the end of this video. Thank you for watching. I hope this helps. Make sure you hit the like button, please, and subscribe, and turn the bell on to get notifications every time Rish or I post a new video. And if there's any other videos you would like to see, any other subjects, concepts, let us know. We're always happy to help y'all. Thank you. Bye-bye.